Okay, so you're going to be finishing out this homework with the last part, part D. We're going to be showing why the transfer functions with complex poles must have parts of complex conjugate residues and poles. Derive how non-repeating pairs the partial fraction terms yield a time domain response of this term we have here. So essentially, we're going to be deriving some functions and coming up with this function right here. We're then going to explain how the time response of a transfer function relates to its poles, purely real versus complex, and negative slash positive real parts. Um, Okay. I'm gonna essentially gonna be doing these both hand in hand. We're gonna kind of see them together and how they all work together, and that's kind of the way I'm gonna be explaining it today. So starting off with our transfer function, we're gonna kind of bring upon that function that we worked on in our previous part, which is g of a function as a function of s, or transfer function, uh, multiplied by a times omega over s squared plus omega squared. And this is going to be equal to essentially our it's going to be equal to a1 over s plus b1 plus a2 over s plus b2. And then essentially this is eventually going to be added by our cs plus d over s squared plus w squared. Okay. So essentially what we want to do now is set up a partial fraction expansion here. And we want to do it for this term right here. So when we do that, what we get is C plus DJ, which is essentially our complex number that we introduced before, C plus DJ over S plus parentheses A plus BJ. Again, we're doing a partial fraction expansion. So this is going to be added by C minus DJ over S plus A minus BJ. Okay. Essentially, these are both our complex conjugate pairs that we have here. So just gonna go ahead and note that complex conjugates, and then we can move on. Okay, so what we want to do now is set up our transfer function for our process side. So this is going to be defined as GP equal to A1 over S plus B1 plus A2 over S plus B2. And we're going to want to set up kind of some conditions. So we're going to state that if B1 is real, and this is going to kind of come into part of our loops, sorry, of our poles of purely real versus complex, and which ones are negative and positive parts. So B1 is real, then essentially what we get is um, A1, A1 e to the negative B, uh, B1t, okay? And if B2 is real, essentially what we get is decay, okay? All right, so from this point, we can kind of set up two things. We can say that for this one, uh, for negative P1, this is essentially our first pole, and this is our second pole, pole two. Okay. All right, so I just wanted to kind of define some other things. We can also say that RHP, which was defined in our problem statement, this is our right-hand pole, okay? So I'm gonna go ahead in a second and kind of draw out a sketch of this, but our left hand is, of course, just our left-hand pole. So coming back to this, essentially what we want is we want our poles to be negative. So more or less, that's key in this. And let's go ahead and draw out a sketch for this. And we have our imaginary right here and our real right here. We also have our left, sorry. Oh man. Okay. Yeah, that works. We have our left hand pole and we have our right hand pole. Essentially for this area, this side right here on our left hand side, we're gonna say that this is negative, our negative portion, right? And remember what we said, the left-hand side of this is essentially what's key in this kind of gray area right here of our top left quadrant is going to be our imaginary, our bottom left quadrant is going to be our real, and essentially um, our left-hand poles in this case, um, which will essentially give off more decay per se, will be essentially better for decay, will essentially be better for stability. So anytime we have a purely real pole, it will give us the time response of um of this function right here. Let me go ahead and circle it of this function right here. Okay. So one other thing to look at is when we have decay or growth, let's go ahead and draw out a graph that will kind of somewhat show this, but we have this right here. And as we have oscillations that slowly decrease, this is known as exponential decay. Again, we want this. Now give it another case where we have our oscillations slowly growing bigger. That's not that great, but we can kind of see um, our growth and decay from these oscillations. This is what we don't want. Okay. All right, so we may have to come back as we're deriving to see if I kind of missed on anything, but essentially, this is more or less the kind of the explanation of our poles and kind of how it affects our growth uh, function or our decay function. Okay, so now we're gonna rewrite our equation for the transfer function of our poles. Let's go ahead and change this. So we have GP equal to C plus DJ over S plus A plus BJ. Again, I did this earlier in the video. I want to get, there you go. Okay. Plus C minus DJ over S plus, this is a lot better, increase the thickness of the pen, S plus A minus BJ. And now what we want to do essentially is do an inverse Laplace transform of this function right here, the transfer function of our process, to essentially get our time domain. So when we do that, we actually get C plus dj multiplied by e to the negative a plus bj multiplied by t. And then this will be added by C minus dj times e to the negative a minus bj times t. Okay. So now that we have that, we can rearrange this to get the domain and pull out all of our e negative terms essentially. So doing this, we get e negative at, and then put some brackets here. We get c times e to the bjt plus e to negative bjt plus dj times e to negative bjt minus e bjt. Okay, so we want to then again rewrite this, calling in our sine and cosine functions. And this will kind of get us a step closer to that function that we actually saw in the problem statement. So doing that, we get e negative at to c multiplied by 2 cosine bt plus dj negative 2j sine bt. Okay. Okay, so now what we want to do essentially is pull out our 2 out of this function. Doing that, we get 2e negative at, and will be again very similar. So c cosine bt plus dj negative sine bt. Okay. From this point, we want to show an expression as a phase lag. To rewrite in terms of pi, essentially. So we're going to be rewriting this in terms of phi, sorry. Doing that, we get 2e negative at multiplied by a sine times bt plus phi. Okay, essentially, this is our final equation. Before we move on, before you finish this, actually, we want to look at just a few constraints, which is a sine phi equal to c and a cosine phi equal to d. This is kind of the two functions or variables we were looking at. And from this, we know that a equal to c squared plus d squared. And yeah, just some constraints that we want to look at. But yeah, so this is their final equation. Oh, no. So this is our final equation. And if you look at what we have here, let's try to see. So we have this response of a negative at sine omega t plus phi. So essentially it's the same thing except that we pulled out with 2. That is the only difference. However, our omega, we can simply just say that omega is equal to b in this case that we introduced here. Let's go back down here. Um, if our omega is equal to, if our b is equal to omega, this is essentially the same equation except for the 2. So yeah, that completes this final part of the homework. And we can go ahead and move on to homework 5, our last one.